Hello, MCU. I'm presenting the final solutions of the project. So in here, I'm doing a Uniaxial tensile test for my samples. So the first thing is about the fabrication. As there are three materials choices, you can, I think all of them can use 3D printing, which is the additive manufacturing to fabricate those parts for the uniaxial tensile test. For example, the stainless steel, you can use selective laser melting, and for the ceramics as well as polymers, you can use the laser to curl the photosensitive resin, and then those parts can be fabricated. Um, and the second thing is the materials model used for this analysis. So in this example, I use a standard dimensions for the actual tensile test as shown here. And I'm considering both of the elastic as well as plastic deformation, but I'm not considering the damage or such as the fraction of these tensile samples. And the materials are defined here. I got four choices. The one is the alumina, which is ceramic, rubber, which is plastic, as well as stainless steel, which is a metal, and the last one is some of the data derived from my experiments, because in my research I actually did lots of tensile stretching as well as compressive test for different kinds of materials. So in these three materials, I just consider a simple elastic deformation of these samples on the uniaxial tensile test. And for this, using my own data, I can consider actually a plastic deformation. And as we can see here, I'm comparing the experiment data as well as the simulation results, and it correlated well. So those are the three materials, and in these three materials we define, because for those elastic, we define the Young's modulus as well as the Poisson ratio. And for my own materials, I define some of the parameters as shown in the Word documents. As I'm actually considering the time rate dependent mechanical properties of my own materials. So I did a fitting from my experiment results, and you can get different parameters from this equation, the Johnson-Cock rate dependence equation. You can get those parameters, and then you input those parameters into the model, and then you will have different you will get a simulation results, so which is showing here for the plastic rate dependent behavior. You basically I got different parameters in here, and by tune those parameters we can achieve different simulation results, and when we compare with the experiment results, we can see which parameters worked really well. And actually for this try, I think the simulation can generate pretty good results. And after defining the materials, we simply assign the materials to the hot blocks, and step 2 is apply the load. So the load is I consider a constant load along the y direction, which is the situation during the tensile test. And for here, the force can be changed. So I got two choices. The first one is 3,000, and the second one is 40K. And also here is the amplitudes when we apply the load. As you can see here, the time frequency as well as the amplitude. And the last one is the boundary conditions. So the boundary conditions are showing here. This whole part was divided into several regions because for here is the stretching region, and that's two ends or the fixed region because those materials are actually fixed by the gripper during the tensile test. So it's not allowed to move. And for here, the top surface, we have a reference point. So which means this whole surface will move together. And that's basically the setup of the uniaxial tensile test. And um, after running the job, we can have the results. And the results is showing in here. I got three different materials. So the first one is the stainless steel. As you can see here, under 3000 Newton, it actually have a very small strain, which is in the elastic range. But it is quite different for the rubber materials because it's much softer than stainless steel. See, the Young's modulus is just 0.03 gigapascal. So under the same load during the stretching, you will have a much higher stress as shown here. It can reach 200, and for the aluminum it's quite close to the stainless steel because the Young's modulus and the Poisson ratio are quite close. And those are the elastic properties of the three materials. The second part is considering my own materials using the experiment data. So here, as I mentioned, we define those parameters from fitting the experiment data to the Johnson curve and rate dependent equation. And those are the parameters defined in here. And after that, we apply a load of 3000 Newton to the stretch sample. And here's the results. Actually, the strain is very small, which is in an elastic range. But when we further increase the load to 40k Newton, you will see the results is a combination of the elastic as well as the plastic behavior. So I compared the simulation results with the experimental results. It correlated to the wear, so which means we can extract the fitting parameters from the experiments, and after that we can using the simulation to evaluate the properties, the mechanical properties of the part. And as you can see here, it actually worked well. So that's generally the whole process of the project. And another few questions to discuss in here is it's kind of a future work. So we may implement a criteria for the dynamic failure analysis by defining the damage parameters so that we will know when where the part will fail. So that is really important for the structure design. When we apply the load to the structure materials, we can know when it will be damaged, which is very important. And the second thing is about the fabrication, because if we use additive manufacturing, the wear have lots of porosity currently in the part, so that will have a big difference, big impact to the mechanical properties of your samples. For example, if you have a high porosity in here, it will make your sample more sensitive to force, and that means it can fail quickly compared to the parts that fabricated by traditional methods. So in that way, we somehow have to change the fabrication process or either make the additive manufacturing more realistic to trying to reduce the defects during the fabrication process to improve the material properties. Yeah, so that's all for the final project. Thank you.